Welcome to Science Salah Lotfy Channel, where science meets clarity and inspiration. Today we take a moment to highlight and appreciate a remarkable contribution to scientific literacy in the Arab world, made by none other than Dr. Osama Gad. Dr. Osama Gad, known on social media simply as Osama Gad, has once again offered his audience a window into the world of advanced science by sharing a powerful excerpt from a recent medical physics publication. The excerpt comes from Chapter 5 of the book titled, What is Medicine? Basic Principles of Physics in Medicine and Beyond. Published by Springer, and written by the Ukrainian author Professor Alexander V. Chalyi, from the Department of Medical and Biological Physics and Informatics at Bogomolets National Medical University in Kyiv, Ukraine. The chapter shared is titled, Thermal Radiation of the Human Body and Its Medical Application. It was published online for the first time on February 21, 2025, and spans pages 135 to 166. This chapter delves into a fascinating area of study: how the human body emits thermal radiation, and how this natural emission can be used for medical diagnosis and treatment. From fever detection to advanced imaging and disease monitoring, thermal radiation plays a pivotal role in today's medical technology. By sharing this kind of knowledge with the public, Dr. Osama Gad continues to serve as a bridge between complex scientific research and the everyday reader, enriching minds and encouraging a culture of scientific curiosity and understanding. And so, on behalf of the entire team at Science Salah Lotfy Channel, we extend our sincere thanks to Dr. Osama Gad for his continued efforts to promote scientific culture through his Facebook page. We deeply appreciate his dedication to education and public enlightenment. May Allah accept from him and from us all our good deeds, and may he grant us all knowledge that benefits humanity, and bless us with abundant provision and enduring success. If you found this video insightful, don't forget to like, share, and subscribe to Science Salah Lotfy Channel, where science is made accessible, inspiring, and truly global. We are all familiar with the feeling of warmth radiating from a hug, a crackling fire, or a sun-drenched beach. But what about the heat radiating from our own bodies? This invisible aura, a constant symphony of infrared radiation, is more than just a byproduct of being alive. It's a unique identifier, a fingerprint of our metabolism, and a window into the complex machinery that keeps us ticking. Think of it. We walk around emitting heat like tiny, fleshy furnaces. This warmth, invisible to the naked eye, reveals a hidden world, a landscape of temperature variations that tell a story about what's happening beneath the skin. And just like that crackling fire, our body's heat is a form of energy, a testament to the constant dance of atoms and molecules within. But unlike a fire, our bodies are exquisitely designed to regulate their temperature, maintaining a delicate balance between heat production and heat loss. This balancing act is crucial for our survival, and the subtle fluctuations in our thermal radiation can offer clues about our health and well-being. So, let's delve into the fascinating world of human body heat and uncover the secrets it holds. Thermal radiation, simply put, is the emission of electromagnetic waves from any object with a temperature above absolute zero. That means everything around us, from the icy depths of space to the steaming cup of coffee on your desk, is constantly radiating heat. The hotter the object, the more intense the radiation. The human body, with its average temperature hovering around 98.6 degrees Fahrenheit, emits most of its thermal radiation in the infrared spectrum. This invisible light, with wavelengths longer than visible light but shorter than microwaves, is what allows thermal imaging cameras to see our body heat. But here's where things get interesting. The intensity and pattern of our thermal radiation aren't uniform. Different parts of our body, from our core to our extremities, radiate heat at varying rates. This thermal landscape is influenced by a host of factors, including blood flow, metabolism, and even underlying medical conditions. You might think that our bodies, like any warm object, would simply cool down exponentially over time, but our physiology is far more complex than that. We are not inanimate objects passively radiating heat. We are living, breathing systems with sophisticated mechanisms for regulating our internal temperature. Instead of a simple exponential decay, our body temperature exhibits a fascinating pattern of damped oscillations. These fluctuations, often subtle and rhythmic, are a testament to our body's remarkable ability to maintain a stable internal environment. This intricate dance of heating and cooling is orchestrated by a network of thermoreceptors, tiny sensors distributed throughout our skin and internal organs. These sensors constantly monitor our temperature and relay this information to the hypothalamus, the body's internal thermostat, which then fine-tunes our heat production and loss mechanisms to keep us within a narrow, life-sustaining range. Section 4. The math behind the heat equations tell a story. As with many biological phenomena, the intricacies of human thermoregulation can be described, at least in part, through the elegant language of mathematics. A second-order differential equation, a staple in physics and engineering, can be used to model the dynamic changes in skin temperature over time. This equation takes into account key parameters like the body's relaxation time, the period of temperature oscillations, decay, coefficients, and frequencies. By analyzing these variables, researchers can gain insights into the underlying physiological processes governing our body's heat regulation. Interestingly, the study of thermal radiation and its connection to human physiology has deep historical roots, intertwined with the revolutionary discoveries of quantum mechanics in the early 20th century. The work of physicists like Max Planck and Albert Einstein, who laid the foundation for our understanding of energy quantization and the interaction of light and matter, also paved the way for advancements in thermal imaging and our ability to see the body's heat. Section 5. Seeing the unseen. Thermography and the diagnostic revolution. Imagine being able to peer beneath the surface of the skin, not with X-rays or scalpels, but with a camera that detects the subtle variations in body heat. This is the promise of thermography, a non-invasive diagnostic tool that's rapidly gaining traction in various fields of medicine. Unlike traditional imaging techniques that rely on external radiation or contrast agents, thermography harnesses the body's own thermal radiation to create images. This makes it a safe and painless option for patients of all ages, including pregnant women and young children. But thermography's appeal extends beyond its non-invasive nature. It offers a unique window into physiological processes, allowing clinicians to visualize inflammation, circulatory issues, and even early signs of disease that might not be detectable through other methods. The cosmos is awash in a symphony of light, much of it invisible to our eyes. We perceive only a sliver of the electromagnetic spectrum, from red to violet. But beyond red lies a hidden realm, the infrared, where temperature paints its own vibrant tapestry. Everything in the universe, from distant stars to the chair you're sitting on, emits some level of thermal radiation. This invisible glow is a fundamental property of matter, a constant hum of energy whispering secrets about the universe's temperature. All matter is composed of atoms and molecules in constant motion. This motion represents thermal energy, and the hotter an object, the more vigorously its particles dance. Imagine a blacksmith heating a piece of iron. As the metal heats up, its color shifts from dull gray to fiery orange and then to blinding white. This visible glow is just the tip of the iceberg. The heated metal also emits a torrent of infrared radiation, invisible to our eyes but detectable as heat. Even at everyday temperatures, objects radiate heat, albeit at lower frequencies and intensities. We are, in essence, walking infrared lamps, radiating heat into our surroundings. The human body, with its internal engine constantly churning, produces a significant amount of thermal energy. This energy needs an outlet, and radiation provides a passive and continuous way for our bodies to shed excess heat. While we lose some heat through conduction and convection, radiation plays a crucial role in maintaining our thermal equilibrium. The infrared radiation emitted by our bodies peaks in the long-wave infrared region, with wavelengths around 10 micrometers. Factors like blood flow, metabolism, and even emotional state can influence these thermal patterns, making infrared imaging a valuable tool in various fields. Imagine looking at the world through an infrared camera. Instead of seeing reflected light, you would perceive objects based on their heat signatures. Humans would appear as glowing figures against a cooler background, their warmth betraying their presence even in complete darkness. But how much heat do we actually radiate? In the late 19th century, physicists Joseph Stephan and Ludwig Boltzmann developed a fundamental law that quantifies this thermal glow. The Stephan-Boltzmann law states that the total energy radiated per unit surface area of a black body is directly proportional to the fourth power of its absolute temperature. This law provides a powerful tool for estimating the radiative power of any object, including the human body. By plugging in the average skin temperature of a human, approximately 37 degrees Celsius or 310 Kelvin, we can calculate the total power radiated. A typical adult human, with a surface area of about 1.8 square meters, emits roughly 1,000 watts of power through thermal radiation. The net heat loss or gain depends on the temperature difference between our bodies and our environment, explaining why we feel colder in a chilly room than in a warm one. While the Stefan-Boltzmann law provides a useful approximation, understanding the intricacies of human thermal radiation requires going beyond the ideal blackbody model. In reality, the human body is not perfectly efficient at absorbing and emitting radiation. We are better described as gray bodies, meaning our emissivity, the ability to emit thermal radiation, is less than 1. Several factors influence the emissivity of human skin, including its texture, pigmentation, and moisture content. Clothing also plays a significant role, acting as an insulating layer that reduces heat loss through radiation. Different body parts have varying temperatures and emissivities, further complicating the picture. Blood flow near the skin surface also influences heat distribution, explaining why our cheeks flush when we're overheated or embarrassed. Understanding the nuances of human thermal radiation has far-reaching implications. Thermal imaging, which captures the infrared light emitted by our bodies, has revolutionized various fields. In medicine, thermal cameras aid in diagnosing circulatory problems, detecting inflammation, and monitoring the effectiveness of treatments. Beyond healthcare, thermal imaging finds applications in security and surveillance, building inspections, and even wildlife monitoring. By detecting subtle temperature differences, these cameras can identify heat leaks in buildings, pinpoint individuals in crowded areas, and even track the movements of animals in the wild. From the vast cosmic tapestry to the intricate workings of the human body, thermal radiation provides a unique window into the energy that permeates our existence. By harnessing this invisible glow, we gain valuable insights into the fundamental laws of physics, unlock new avenues for medical diagnosis and treatment, and develop innovative technologies that improve our lives. The sun, a giant ball of burning gas. But it's more than just fire. It's a giant engine powering life on Earth. How? Through thermal radiation. This radiation is energy that travels as waves. These waves bring light and, importantly, heat. Without the sun's thermal radiation, our planet would be a frozen wasteland. Think of standing by a bonfire. You feel the warmth even from a distance. That's thermal radiation. The sun is like a massive bonfire, sending its warmth across millions of miles of space. This energy fuels everything from the air we breathe to the food we eat. Deep within the sun's core, a fiery dance is happening. It's called nuclear fusion. Here, under immense pressure and heat, hydrogen atoms are forced together. They fuse, creating helium and releasing colossal amounts of energy. This process isn't random. It follows a specific recipe, the Bethe cycle. Think of it like baking a cake. You combine ingredients in a specific order to get the final product. In the sun's case, the ingredients are hydrogen nuclei. The oven is the intense pressure and heat of the core, and the cake is the energy that powers the sun. This energy is what fuels the sun and allows it to radiate heat and light outward. It's a continuous process, ensuring a constant supply of energy for billions of years. The sun's energy doesn't just magically appear on Earth, it travels millions of miles through space. This journey isn't smooth sailing. The amount of energy reaching Earth is measured by something called the solar constant. Think of it like the sun's power output. But not all of this energy reaches us. Some are reflected back into space. The energy that does reach us is determined by Wien's law. This law explains why the sun appears yellow. It's like filtering light through a prism. Each color has a different wavelength and energy level. The sun emits a wide range, but we primarily see the yellow-green part of the spectrum. Section 4. Earth's atmosphere, a protective shield. Imagine Earth wearing a giant sunscreen. That's our atmosphere. It filters out harmful radiation from the sun. Without it, life on Earth would be impossible. It's a delicate balance, though. Too much filtering and we freeze. Too little and we fry. The atmosphere is made up of different layers, each playing a vital role. The ozone layer, for instance, absorbs most of the sun's harmful ultraviolet radiation. This protective shield allows life to flourish on Earth, but like a good sunscreen, it needs our protection too. Section 5. Infrared, the heat we feel. We can't see it, but we can feel it. Infrared radiation. It's the warmth we feel from the sun or a warm stovetop. This radiation exists on a spectrum from near infrared to far infrared, each with different wavelengths and energy levels. Think of a pot of boiling water. The water closest to the heat source is the hottest. That's like near infrared radiation. As you move further away, the water cools down. That's similar to far infrared radiation. Each zone has its unique properties and applications. Section 6. Infrared and us, from healing to technology. Infrared radiation isn't just about feeling warm. It has numerous applications in medicine and technology. In medicine, it's used for thermal imaging to diagnose illnesses. It's also used in therapy to relieve pain and reduce inflammation. Think of it like a targeted heating pad. Infrared radiation can penetrate deep into tissues, increasing blood flow and promoting healing. It's a non-invasive way to treat various conditions. Beyond medicine, infrared is used in night vision goggles, remote controls, and even in fiber optic communication. It's a versatile tool with endless possibilities. Hey there, science enthusiasts! Welcome back to the Science Salah Lotfy Channel, where we make complex science crystal clear. At the end of today's episode, we're exploring a fascinating force that surrounds us every day, yet we rarely see it. It's called thermal radiation, the invisible light of heat that every warm object emits, including our own bodies. So, what exactly is thermal radiation? Thermal radiation is a type of electromagnetic radiation that comes from the internal energy of matter. It's generated by the thermal motion of atoms and molecules. As long as an object has a positive absolute temperature, it's emitting thermal radiation. Studying thermal radiation was actually a turning point in the history of physics. It laid the groundwork for quantum mechanics. That's right. Understanding heat and light helped change our understanding of the universe. One of the most important sources of thermal radiation is the sun. Its spectrum closely matches that of a perfect blackbody, which is an ideal emitter of thermal energy. This radiation has real-world effects, especially in medicine. For example, solar thermal radiation plays a crucial role in treatments and diagnostics. Let's talk about our own bodies for a moment. Scientists have recorded the thermal radiation of human skin in the infrared range, the part of the electromagnetic spectrum associated with heat. Their experiments showed damping temperature oscillations, waves of temperature that slowly decrease over time. Now let's dive into some numbers from Table 5.1-1. The damping decrement dE is 3.167. 1. The logarithmic decrement L is 1.153. 1. The period of damping oscillations is 9 minutes. 1. The damping coefficient beta is 0.128 per minute. 1. The relaxation time tau is about 7.8 minutes. 1. The frequency of damping oscillations omega is 0.698 radians per minute. 1. And the natural frequency OO is 0.710 radians per minute. These parameters help researchers understand how our skin responds to changes in temperature, especially during inflammation or stress. Now here's where it gets practical. When part of the body is inflamed, it gets warmer. Thermal imaging, or thermography, can detect that heat without touching the body at all. That makes it especially useful in early diagnostics. Unlike X-rays, kinetic scans, or MRIs, thermal imaging is completely non-invasive. It uses only the body's natural thermal radiation. No radiation exposure, no injections, just light, invisible heat, from your own skin. That's the beauty of thermography. It's safe, silent, and remarkably insightful. And it all goes back to the science of thermal radiation. So the next time you feel warmth on your skin, remember, you're not just feeling energy, you're emitting it. Thanks for watching for Science Salah Lotfy Channel. If you found this topic intriguing, stay tuned for more simplified science rooted in cutting-edge research. Hey there, science enthusiasts! Welcome back to the channel. Today, I'm shining a spotlight on a remarkable figure in the Arab world who's bridging the gap between global scientific research and the Arabic-speaking community. Meet Dr. Osama Gad. If you haven't heard of him yet, let me introduce you. Dr. Gad is an influential voice in Egypt's scientific scene, and he's been using social media to make cutting-edge science accessible to thousands of Arabic readers. Recently, Dr. Gad shared an excerpt from a groundbreaking book titled, What is Medicine? Basic Principles of Physics in Medicine and Beyond, written by Professor Alexander V. Chalyi. This book, published by Springer, dives deep into the intersection of foundational physics and medical applications. One chapter that caught Dr. Gad's attention is Chapter 5, Thermal Radiation of the Human Body and Its Medical Application. This chapter, published in February 2025, explores something fascinating: how the human body emits infrared radiation and how this can be used in medical diagnostics. Think of it this way: our bodies are like natural emitters of infrared radiation, or heat. This concept, rooted in the century-old study of blackbody physics, is now being used to detect inflammation, vascular issues, and even tumors with technologies like infrared thermography. It's not just theory, it's science saving lives. By sharing this information, Dr. Gad isn't just spreading knowledge, he's making advanced medical physics accessible to those who might not have direct access to international research. This is the power of effective science communication. Dr. Gad's efforts are a perfect example of how science can be democratized. He's breaking down barriers and making sure that cutting-edge research reaches everyone, not just a select few. So, a massive thank you to Dr. Osama Gad for his dedication and for making science both visible and relevant to the Arabic-speaking world. You're an inspiration to us all. Stay tuned as we continue to explore more scientific breakthroughs and how they shape our world. Thanks for watching, and see you next time.